So if you want to measure intelligence, you need to rigorously define what intelligence is, which in itself, it's a very challenging problem. Intelligence emerges from the interaction between a brain, a body, like embodied intelligence, and an environment. Human perception, and not so much about intelligence. There's a big difference between mimicking intelligent behavior and actual intelligent behavior. If you look at the really successful AI systems today, I think they're already hybrid systems that are combining symbolic AI with deep learning. For instance, successful robotics systems are already mostly model-based, rule-based. They're using deep learning as perception modules. The self-driving car is mostly symbolic, it's software, it's programmed by hand. So it's mostly based on explicit models, in this case, mostly 3D models of the environment around the car, but it's interfacing with the real world using deep learning modules. Deep learning is not the road to artificial general intelligence, right? Scaling up deep learning by adding more layers, adding architecture search, using these deeper models or training on more data is not going to get you to AGI. I think intelligence is essentially the efficiency with which you turn experience into generalizable programs. So what that means is it's the efficiency with which you turn a sampling of experience space into the ability to process a larger chunk of experience space.
It's almost as if he's trying to be a contrarian, like saying the emperor's got no clothes, right? He's saying that all of these folks are working on AI systems that are not really intelligent. I think if that was his aim, I think it's been a success.
As a contrarian, I absolutely respect the attempt to be a contrarian.
If you like the conversation today, remember to like, comment and subscribe. I always really enjoy reading the comments. If you want to watch the full discussion that I had with Yannic and Connor about On the Measure of Intelligence, then it will be released on the Machine Learning Street Talk podcast in the next couple of days, so make sure you check that out. Our flexibility and adaptability allows us to operate in situations that differ hugely from things that we've directly experienced before. One of the most surprising things about deep learning is that it works so well. Who would have thought that you can just take some geometric, parametric models, train them with sufficiently large examples, and you can almost do anything? As Richard Feynman said, it's not that the universe is complicated, there's just a lot of it. I think Francois Chollet is one of the pillars of the deep learning community and one of my biggest personal inspirations. He's got nearly 12,000 citations. He invented Keras, which is probably the easiest to use deep learning library in existence. It's now been kind of merged into TensorFlow. Francois has the most amazing Twitter account. He's opinionated and sometimes salty, but I love some of the stuff he posts on there. Here's an example. Conspiracy theories like 5G causes corona, or those promoted by Elon Musk, are boring. I want to see good stories like the virus is actually a growth hacking initiative started by the genetic engineering department at Zoom.
Yeah, no, I think if you go through the trouble of maintaining a Twitter account, you might as well speak your mind, Otherwise, what's even the point of having a Twitter account? It's like having a nice car and just leave it in the garage.
Training even bigger convnets and LSTMs on even bigger data sets gets us closer to strong AI in the same sense that building taller towers gets us closer to the moon. There's more to intelligence than brute forcing the space of everything that may possibly happen, either via rules or via training data. Now this is more relevant to what we're talking about today, which is how do we measure intelligence? I first read his Deep Learning with Python book a couple of years ago, and when I worked at Microsoft and went on customer hacks, I would always bring that book with me like a Bible. I would force everyone to read the first 4 chapters of it, and also the chapter on the limitations of deep learning before I even started cutting any code, because I just think that his no-nonsense approach is absolutely refreshing. One of the first videos I made on Machine Learning Dojo was all about Chapter 6 of Francois Chollet's Deep Learning with Python book. And even back then, as you can see, I hugely endorsed the book because it really is an amazing book.
So this is a huge endorsement from me. I do recommend to buy this book.
In one of the final chapters of Chollet's book, he talked about the limitations of deep learning. And I think Chollet has always been one of the most credible critics of deep learning. He's contributed so much to the field, but he's very straight talking about what you can and can't do with deep learning. This isn't to say that he's denigrating deep learning, but he wants people to be aware of the limitations.
Before it started working, people, considered people working on neural networks as cranks very much. No one was working on this anymore. And now it's working, which is what makes it valuable. It's not about being right? It's about being effective. Around 2013, 2014, I was many times surprised by the capabilities of deep learning, actually.
Right. Yeah.
That was before we had assessed exactly what deep learning could do and could not do, and it felt like a time of immense potential. And then we started, narrowing it down. But I was very surprised.
So in the chapter on the limitations of deep learning, Chollet pointed out that these deep neural networks, they perform a series of geometric transformations, mapping data from one data manifold into another data manifold, successively. Of course, assuming that there exists a continuous learnable transformation from X to Y. In order for that to work, Chollet points out that you need to have a dense sampling of X to Y. So you can think of deep learning models as being kind of like computer programs, but the inverse is not true. Deep learning models cannot represent most computer programs. The reason for that is the corresponding geometric transformation may just be too complicated, or there might not be enough data available.
If you try to learn a sorting algorithm using a deep neural network, well, you're very much limited to learning point by point what the sorted representation of this specific list is like. But instead, you could have a very, very simple sorting algorithm written in a few lines. Maybe it's just, 2 nested loops. And it can process any list at all.
Chollet, even back in 2017, was talking a lot about local generalization versus extreme generalization. So he points out that humans are capable of far more than mapping immediate stimuli to immediate responses, like a deep neural network or maybe an insect. They maintain complex, abstract models of their current situation, of themselves, of other people, and can use these models to anticipate different possible futures and perform long-term planning. They're capable of merging together known concepts to represent something they've never experienced before, like picturing a horse wearing jeans or imagining what they could do if they won the lottery. This ability to handle hypotheticals, to expand our mental model space far beyond what we can experience directly, in a word, to perform abstraction and reasoning, is arguably the defining characteristic of human cognition. And this is what Chollet calls extreme generalization, an ability to adapt to novel, never experienced before situations using very little data or no data at all. So Chollet says this stands in sharp contrast with what deep neural networks do, which is what he calls local generalization. They map from inputs to outputs in a way that stops making sense if new inputs differ even slightly from what they saw at training time.
Deep learning models are like huge parametric models, differentiable, so continuous, that go from an input space to an output space. And they're trained with gradient descent. So they're trained pretty much point by point. They're learning a continuous geometric morphing from an input vector space to an output vector space. Right? And because this is done point by point, a deep neural network can only make sense of points in experience space that are very close to things that it has already seen in its training data. At best, it can do interpolation across points.
He gives the example. So imagine you were learning the appropriate launch parameters to get a rocket to land on the moon. If you were using a deep neural network for this task, whether training using unsupervised methods or reinforcement learning, you would want to feed it with thousands or even millions of launches, because you can only make it work if you expose it to a dense sampling of the input space. By contrast, humans would get the rocket to land on the moon just with a few trials, because they have abstraction and reasoning. They can derive general rules that will work in all situations. They've invented this thing called rocket science. This is the difference between humans and machines right now. Humans can abstractly model hypothetical situations without having to experience them directly. We have our imagination. This allows humans to generalize in an extreme sense. Our flexibility and adaptability allows us to operate in situations that differ hugely from things that we've directly experienced before.
what was really shocking is that it worked, right?
It worked at all, yeah.
Yeah. But there's a big jump between being able to do really good computer vision and human level intelligence. So I don't think at any point I was under the impression that the results we got in computer vision meant that we were very close to human level intelligence. I don't think we're very close to human level intelligence. I do believe that there's no reason why we won't achieve it at some point.
Chollet gives this wonderful metaphor to describe what happens in a deep learning algorithm. Imagine if I needed to classify if a point was on the top half or the bottom half of this bit of paper. Well, it's hard to do because it's crumpled up into a ball. If I could successively uncrumple the paper through layers of geometric transformations, when the paper becomes a plane, then just a simple linear classifier would be able to cut the paper in half and would tell me which half of the page I was on. That's what deep learning does. So anything that's represented as a sequence of continuous transformations, deep learning is really good for that.
And so that may seem a bit abstract, but you can actually visualize this process in 3D by trying to imagine someone trying to uncrumple a paper ball, a crumpled paper ball. It's, in first approximation, you could say its gesture is an affine transform on the paper ball. And although each transformation is very simple, the total sequence of gestures implements a very complex geometric morphing that gets you to this flat sheet of paper again. So basically that gets you to linear separability of your classes again.
There was a paper out very recently from FAIR. It was about applying transformers models to solving complex mathematics. So what these folks did was they took complex mathematical problems, they expressed them using English language. Of course, in many of these cases, you could procedurally generate the data, so you can train this language model. And what was incredible was that these language models could solve sometimes very complex integration problems. And integration is kind of like the art of the mathematics world. Now, were these models actually learning how to do maths and reasoning? The numbers weren't actually fed into the models. They were encoded using tokens, using character-based tokens. So the model had no concept even of the number system. This is a perfect example of the pitfalls of deep learning, because what it's really doing is pattern matching. It's seeing, oh, that there's a cosine here, there's this thing here, there's this thing here. When these things work together, this happens. So the problem with deep learning is it will find surface shortcuts. In computer vision, it might look at the textures. It's not actually doing what you think it's doing. And one of the main problems that Chollet points out with deep learning is the anthropomorphization of deep learning. When humans see a smiley face on the rock, we think that the rock is happy, but machines don't think the way that we think. So Chollet points out that machine learning models don't really understand the inputs in the way that we do. We are earthly creatures. We have all of these sensory inputs and we have this abstract mental model of understanding of the world. Machine learning models don't have that. So when Yannic reviewed this mathematics paper, he asserted that we should be trying to see if the model is actually reasoning. Is it actually following the steps that a mathematician would take? Well, that's almost a rhetorical question. Of course it's not. What we could do is we can try and stop the deep learning models from taking shortcuts. But because we're interpolating through this continuous geometric space, it's impossible to stop the deep learning models taking shortcuts. And this is why Chollet advocates that we should be moving towards some kind of neural symbolic program synthesis. Chollet points this out, that many things that we don't think of as being intelligent, especially collective entities, things like markets or companies or even science as a process, that they are intelligent, but we don't necessarily recognize them as being so.
Human intelligence is specialized in the human experience, and human experience is very short. Like one lifetime is short. Even within one lifetime, we have a very hard time envisioning, things on a scale of years. Like it's very difficult to project yourself at a scale of 5 years, at a scale of 10 years, and so on.
Right.
We can solve only fairly narrowly scoped problems. So when it comes to solving bigger problems, larger scale problems, we are not actually doing it on an individual level. So it's not actually our brain doing it. We have this thing called civilization, right? Which is itself a sort of problem-solving system, a sort of artificial intelligence system, right? And it's not running on one brain, it's running on a network of brains. In fact, it's running on much more than a network of brains. It's running on a lot of infrastructure like books and computers and the internet and human institutions and so on. And that is capable of handling problems on a much greater scale than any individual human. If you look at computer science, for instance, that's an institution that solves problems, and it is superhuman, right? It operates on a greater scale. It can solve much bigger problem than an individual human could. And science itself, science as a system, as an institution, is a kind of artificially intelligent problem-solving algorithm that is superhuman.
Francois seems to think that current machine learning methods are brittle and data hungry. They don't generalize very well, either from the training data that they were trained with or from the assumptions of their creators. They can't really deal with novel tasks. And there's been a real focus on narrow-based skill as opposed to generalization.
Well, if you look at different benchmarks for intelligence today, they're all too focused on skill at a given task, like skill at playing chess, skill at playing Go, skill at playing Dota. Mm-hmm. And I think that's not the right way to go about it, because you can always beat a human at one specific task.
So let's look at the abstract for the paper. Chollet thinks that we need to have an actionable measure of intelligence. There have been many attempts to define intelligence so far. They need to be comparable with each other. He thinks that almost all measures of intelligence now and machine learning approaches have focused on measuring skill, and skill can be bought with unlimited priors or unlimited training data or experience. An example of a prior is in a convolutional neural network. You impute kind of domain knowledge into the system. So CNNs know that pixels have a local connectivity, that they have a spatial relation. So what you're doing essentially is you're encoding knowledge into the system. Chollet thinks that any measure of intelligence should account for that pre-coded knowledge. He thinks that a lot of the skill-based methods now can be bought, but just by throwing lots of computation at the problem. Chollet wants our conception of intelligence to become more human-like. He advocates for an anthropocentric measure of intelligence and disavows universal intelligence. Deep learning methods have been an absolute revolution, and it's difficult to argue with their impact and success. Undeniably, deep learning methods have allowed us to move away from needing to be domain experts. In the olden days, we used to have to explicitly craft all of the logic and code in a system. Deep learning methods, they offer a universal computational paradigm that allow us to apply it to almost any problem, and we don't need to be domain experts in the same way that we used to be. Chollet argues that modern machine learning approaches lack flexibility and generalization. He thinks that we've been too focused on evaluating models by skill. Chollet points out that it's testimony to the immaturity of our field that the question of what we mean when we talk about intelligence still doesn't have a satisfying answer. Now, what's more complicated? Solving the game of Go with artificial intelligence, or picking up the phone and talking to your mother? It might surprise you to learn that it's the latter. Just think about all of the skill programs that you would need to write to pick up the telephone in any room. Natural language processing, speech recognition, various different forms of dialogue processing, and so on. It's far more difficult to pick up the phone and talk to your mother, and that's counterintuitive. So Chollet talks about this really interesting lineage from, the 1980s when we had expert systems. And there was no concept of learning. If you looked in any textbook on artificial intelligence in the 1980s, the word learning wasn't even in the book. Back then it was the paradigm of expert systems. That was the modus operandi. And a great example of that was the Deep Blue computer program that beat Garry Kasparov at chess. Now, this was an example of the kind of priors that Chollet is talking about. The creators of Deep Blue imputed all of the rules and all of the heuristics into the algorithm. The algorithm was brute force searching ahead of time. Of course, it had to do some pruning of the tree, because even in chess, there were a huge amount of potential future board configurations. So there was some minimax tree thing going on with pruning. But the point still remains that we couldn't possibly have known in the 1970s that if we built such a chess program that could beat a human, it wouldn't actually be intelligent. We assumed that to play chess, you need to have planning and reasoning and abstraction. But what we didn't realize was that humans need to have that. So Chollet would argue that Garry Kasparov is intelligent not because he has the skill of playing chess, but because he learned how to play it in an efficient way, and the skill program taxonomy that he developed to play chess has much greater generalization power than Deep Blue did. Now, Chollet still thinks that we're barking up the wrong tree now. In a way, if you look at AlphaGo, for example, that is brute force learning. So undoubtedly less priors are imputed into the system than were the case with Deep Blue.
Like, why do we think Magnus Carlsen is smart? Why do we think someone like a Go master is very intelligent? And that's because we know that this person is human. At least we believe. There are doubts about some of these grandmasters, but we believe that they are humans, and therefore we know that they have only had, 20, 30 years to learn this, and they must eat regularly, and they can only think so fast, and it's hard to memorize things as a human. So we know all of their constraints that went into learning this, and we basically know it's not like we are not aware of something like Neo has in the Matrix, where you can just upload the solution to chess into your brain. We know what's required to achieve that level of success, and we know the only way this can be done is through general intelligence. We know that there is this correlation in humans that if you are good at chess, you must have this, or you're very, very likely to have this general problem-solving ability, right? That's a human-centric view, and that does not count for machines. Machines can take forever to calculate. They can distill years and years of experience, like thousands of years. And this would be the same case with these OpenAI Dota 5, right? Dota 5 is exactly here. AlphaGo is exactly here. We only think they might be intelligent if a human does it, because we know what's required for humans to get there.
Chollet also says that there have been two divergent opinions of intelligence throughout the ages. One is Locke's tabula, which is blank slate. And this is the current kind of zeitgeist of thinking, even in the deep learning world, that the human mind or even a deep learning model is a blank slate and it can be trained from experience. The other model of thinking is that things are very much baked in, and this was Marvin Minsky's conception of artificial intelligence. They thought that the problem of intelligence was about being able to encode human behavior into subroutines and being able to store knowledge in an explicit knowledge graph. So learning at the time was discounted as pure memorization. The word learning only appeared in textbooks in the late 1980s when machine learning started to come into the fore. So you have this two kind of dichotomous camps of thinking.
Measuring intelligence in humans is difficult enough. Chollet here is trying to come up with a measure in machines, and that's a pretty daunting task.
Chollet goes on to categorize 4 types of narrow-based skill evaluation that we have now. Peer confrontation, so that's basically what AlphaGo is. Human review, so that would be something like the Turing test, when you rely on humans to test what you're doing.
I actually don't like the Turing test because it's very lazy. It's all about completely bypassing the problem of defining and measuring intelligence.
White box analysis and also benchmarking. Benchmarking is the current modus operandi for machine learning. And if you think about it, having a static benchmark is wonderful because it means that you can compare tests, you can have competitions, you can do non-interactive evaluation and various statistical measures of success and validity. It's worked really, really well. But Chollet points out that on Kaggle, things haven't always gone well. You have this kind of benchmark hacking phenomenon, and many of the competition winners are so highly tuned that they don't even generalize to real-world instances of the same problem. So Chollet points out that optimizing for a metric or even a set of metrics will inevitably lead to shortcuts. He also points out McCorduck's AI effect. And this is really interesting because there isn't really an agreed definition of intelligence. And some definitions of intelligence even include the word intelligence as part of the definition, which is very esoteric. And the McCorduck effect is that every time you create something which is called intelligent, there'll be a chorus of people who will say, oh, that's not intelligence. And actually, a lot of people joke that the definition of artificial intelligence is if we don't understand it, it's artificial intelligence. So it does rather beg the question that we'll never really invent artificial intelligence because some people will keep moving the goalposts. And this is one of the criticisms that Yannick had on the Measuring of Intelligence paper, that Francois has these 4 levels of generalization. Local generalization is what machine learning algorithms are now, and then so-called broad generalization. So an example of that would be solving Wozniak's coffee cup challenge. And that's when you can have a robot that could go into any single room and make itself a cup of coffee. Now, Yannick just thinks that's moving the goalposts because even when you solved Wozniak's coffee cup challenge, he would just say, oh, that's not broad generalization. You've cheated or you've taken a shortcut.
Machine learning in general is the science of generalization. You want to generate knowledge that can be reused across different datasets, across different tasks.
So what's generalization? Generalization is the broad ability to handle tasks that differ from previous tasks. So you have a task and it's different from previous tasks, you generalize. Now there are 2 ways you can view this. There is system-centric generalization, and that's basically if you take the strict definition here. So this would be a machine learning system trains on the training set and then is evaluated on the test set. It has never seen the test set before, so it's generalizing, right? That's called system-centric generalization. But that's not really enough here because we also need to take into account the developer of the system. So developer-aware generalization means that you generalize to situations that are new to the system and to the developer. So a developer of an ImageNet model knows that it is going to be evaluated on the ImageNet test set. And that is in this category, system-centric, because the developer knows. However, a broader generalization, this developer-aware generalization, also takes into account that fact, and it would say developer-aware generalization is only when the system generalizes to something that is not known to developer, that is new to even to the developer themselves. They haven't foreseen that. So this accounts for prior knowledge of the developer.
So coming back to this notion of generalization, Chollet formalizes 4 levels of generalization. The absence of generalization, so that might be something like a sorting algorithm. Local generalization, so that's all of the machine learning algorithms. Broad generalization, so self-driving cars or the Wozniak coffee cup challenge. He then goes on to say that extreme generalization is what we do as humans. So that's being able to deal with the unknown unknowns, being able to have a really broad adaptability to situations that we've never experienced before.
So this is the general diagram that also emerges from kind of theories of intelligence from psychology, where generally you have a general intelligence factor, which is one factor. This is quite remarkable in humans. There is one general intelligence factor statistically. All these general intelligence tasks, they broadly correlate and lead to one statistical factor. It's not obvious why that should be, but it turns out to be one factor that distributes hierarchically into these things, which are called broad abilities, broad cognitive abilities. And in Chollet's framework, that would correspond to broad generalization. And then these are again hierarchically subdivided and sometimes, as you can see here, shared task-specific skills. Okay, and this in Chollet's framework would be local or no generalization.
So here's a simple number sequence. This is a number sequence. Well, it would be, if it was in an IQ test, it would be a very simple question in an IQ test. But it's just to illustrate the point here. So you could be sitting an IQ test, you see the sequence, and you think, what happened? What's the next? What's the correct answer? Well, maybe the rule is 2n minus 1. So it's basically just counting through the odd numbers, right? Okay, another possibility. Maybe it's this equation. Now, if you want to do the math, you see when n is 1, that goes to 0, so that factors out, that goes to 0. When it's 2, that goes to 0, that 3. And then once it's gone past this, the whole thing then, so it's just following this rule to start with, then it jumps up to 33. So maybe the correct answer to this is 33, right? Because, we have a rule that explains all the data we have. No, that's wrong. You'll fail your IQ test. So why is it, given that both of these work for all the data we have, why is it this is considered the right answer? It's a philosophical principle called Occam's razor. And basically what it says is, there are many different explanations of things, but the most likely one is probably the simplest one.
One of the kind of controversial things that Chollet says, and we'll get into this in more detail, that there was Legg and Hutter in about 2007, they wrote a paper which was formalizing a definition of general intelligence. And it was completely different from Chollet's conception.
Are machines actually becoming more intelligent? Some people say yes, some people say no. It's not really clear. We know they're getting a lot faster at doing computations, but are we actually going forwards in terms of general intelligence? So I put together, I believe, the world's biggest collection of definitions of intelligence. I have like nearly 80, I think. There are as many definitions of intelligence as there are people who define it, basically. First of all, it's a property of some sort of agent. It interacts with an environment so as to successfully achieve goals across a wide range of environments. And I think these are 4 very basic fundamental things that you see coming through in a lot of definitions. And they're quite simple ideas. So what I wanted to do is I wanted to come up with a formal definition of intelligence, right? I wanted to really nail this down so I can start, measuring how smart my algorithms are and stuff. So we now have our 4 things here that we originally had, and we have Occam's razor added to it. And now we have enough to go and formalize this definition. We have all the bits we require. So, ta-da! Here is an equation for intelligence.
Shane Legg actually had a great presentation on YouTube. So the measure of success, this is for one agent, and it's a function of the success valued over all of the environments, but the value is weighted by the complexity of each individual environment.
Exactly. This implicitly sort of assumes the distribution of environments around us, right? And it goes over, I don't know what the scope of environment here is, but I think that's what Chollet's definition would be disagreeing with here, that the scope of environment needs to be the human environments, because even if an environment is like very simple or very complex, it doesn't matter if it's not relevant to us. And I tend to agree with Chollet on this particular part.
And Chollet explicitly says that he doesn't like what Legg and Hutter came up with. But Legg and Hutter's definition is what's being taught in universities now. If you look at the latest DeepMind set of lectures, they were teaching it in UCL just a few weeks ago, and they were teaching Legg and Hutter's definition. And we'll get to that. But Chollet thinks that intelligence should be anthropocentric. Chollet thinks that all intelligence is related to a scope of application. General AI should be benchmarked against human intelligence, and that there's no such thing as universal intelligence.
I also believe that, it's the problem with talking about human level intelligence is that implicitly you're considering like an axis of intelligence with different levels. Right. But that's not really how intelligence works. Intelligence is very multidimensional. And so there's the question of capabilities, but there's also the question of being human-like. And it's 2 very different things. Like you can build potentially very advanced intelligent agents that are not human-like at all. And you can also build very human-like agents. And these are 2 very different things, right?
He argues that human-like general intelligence should be founded on explicitly described knowledge priors. And knowledge priors are things like arrows or dogs or things that human beings just understand to be a thing.
Chollet makes his framework particularly human-centric, arguing that
intelligence can't just be whatever. Intelligence should be measured against human intelligence. And therefore, if we build machines that are supposed to be intelligent, we should endow them with priors that humans also have, which means things like the ability to navigate in 2D and 3D environments, the basic understanding of counting and numbers, and also kind of a pre-programming about social cues and social interactions. Anything other than that just means that the machines would have to catch up first with the humans in that, and anything on top of that would be unfair to compare them to humans. Since human intelligence is the only intelligence we're aware of, it very much makes sense to view intelligence in a human-centric way. On top of that, if you view intelligence in an agnostic general way, the no free lunch theorem immediately comes to mind.
In some prior knowledge that's innate, that we have at birth, knowledge about things like agents, goal-driven behavior, visual priors about what makes an object, priors about time, and so on. That shows also in the way we learn. For instance, it's very, very easy for us to pick up language. It's very, very easy for us to learn certain things because we are basically hard-coded to learn them.
Now, one of the main things that Chollet did in this paper was he introduced a new type of challenge and corpus. It's called the ARC, the Abstraction and Reasoning Corpus. Now, this is kind of like an intelligence test, right? But the difference is that there's more diversity of tasks. There are many, many, many different tasks, and almost every single one of them is novel. The other thing is you only get 3 examples of what to do. So it's very, very similar to a human psychometric evaluation. And this kind of fits in with Chollet thinking that there should be an anthropocentric view of artificial general intelligence. Now, the difference from traditional psychometric tests is that there should be much more novelty, because we don't want the systems to learn shortcuts or, be able to leak information between the tasks. But he does think that we should impute core knowledge into the solution. So things like understanding about contiguity and line drawing and homogeneity and goal-directedness and so on. Now, he specifically says that he did not procedurally generate these tasks because if there was some static master program, it would make it much easier to reverse engineer.
We can definitely build systems that start from the same innate priors as what humans have at birth, because we already understand fairly well what sort of priors we have as humans. Like, many people have worked on this problem, most notably Elizabeth Spelke from Harvard. I don't know if you know her. She's worked a lot on what she calls core knowledge. And it is very much about trying to determine and describe what priors we are born with.
So the only way to solve the ARC that I can think of would be to put my mind into the mind of Chollet and to try and think, what would he do? It's worth noting as well, by the way, that Chollet designed the ARC challenge specifically to test developer-aware generalization. So any solution that I create, any meta-learning algorithm, couldn't possibly know about the task in advance. So this is one of the ARC challenges that Chollet proposes. It's reasonably easy from a human point of view because we have all of these priors that are built into us. Things like symmetry, objectness, contiguity, goal-orientedness. Now, when we look at this, as a human, I can immediately spot the symmetry. We are given 3 examples of one grid leading to another grid, and the label, the thing that we're trying to predict, is the masked black region in the first grid. So that goes to that, this goes to this goes to this, as this goes to what? Now, from a machine learning point of view, this is quite difficult. It's difficult because we're only given 1, 2, 3 examples. Normally, in machine learning, we're given hundreds of thousands of examples or more. We're trying to come up with a meta-learning algorithm that will give us a function which will generalize to many, many unseen examples of this phenomenon. That is super difficult. This is definitely the hardest Kaggle challenge that has ever existed. There's no question about that. It might be instructive for us just to go through how we as humans would solve this problem. Now, we would look at this and we'd say, oh yeah, there's some symmetry. There's some symmetry. So if I started to write some code here, what would I do? Well, I would do something like this. So yeah, this is a little bit like a coding challenge at Google or something like that. So let's start off with a 4x4 grid. And maybe some of the cells, so we're going to go really easy here. We're just going to use one color, just red. And there's a symmetry here, which means over on this side, we also have red. Now imagine that this part of the grid was blanked out, and we wanted to predict this grid cell. What would it be? Well, of course, it would be this. So what we're doing is we're mapping this to this, this to this, this to this, and this to this. So that means we're mapping 0, 0 to 3, 3, 0, 1 to 2, 3, 1, 0 to 3, 2, and we're mapping 1, 1 to 2, 2. Now what does this depend on? Well, it depends on the width and the height of the grid. So let's try and figure out what's going on here. So 0 goes to 3, so that is the same as saying 0 goes to width. 1 goes to 3, that's the same as saying 1 goes to width minus 1. So it's reasonably straightforward what's going on here. So what we need to do is say f of x is equal to width minus x, and f of y is equal to height minus y. So far so good. So if we were to write a Python function to do this, what would it look like? So it's reasonably intuitive. We would have two nested for loops, right? So we would say for x in x, for y in y, and then the first thing we would do is figure out if we're on a black grid cell. So we'd say if grid of x, y is equal to black, then what do we do? Well, the first thing we should do is figure out where the top and left coordinate is. So we can say min x min y is equal to 0. And then here, if we are stepping into the black grid, then we know where the top left coordinate is. So we can say if min x is equal to 0, then min x is equal to x, min y is equal to y. Okay, so we've done that. Now all we need to do is start to copy over the cell in this black grid to the output grid. So we've got our output, and we can say the output. Now we need to know what the coordinate of that output is. So that will be x minus min x, y minus min y is equal to the grid, and then this is the function that we learned before. So it's width minus x and height minus y. Now, this is the program that personifies what humans would do. I've gone through this thought process and I've come up with an expert system. I've come up with a logical set of rules or symbolic reasoning that I know would analytically generalize to every possible permutation of this particular problem. If we tried to do the same thing with a machine learning algorithm, it wouldn't work. It would just take shortcuts. Well, first of all, it wouldn't work because there isn't a sufficiently dense sampling of the input space. We only have 3 examples. But even if I procedurally generated hundreds of thousands of examples, it would just learn a trick. And it would learn a trick because all deep learning is doing is interpolating in this kind of geometric continuous space. It's just so easy for deep learning algorithms to find patterns. It's not learning the set of rules that we want it to learn. It's worth pointing out here that I'm assuming that the width of the black grid is known. Of course it's not known, so what you would actually do is when you enter into the black grid, you would have 2 for loops that would go to the right and go below to figure out the width and the height. So that's just something that I've left out for brevity, but you get the idea.
And that's what I find so interesting about this ARC challenge. Like, I really disagree that solving the ARC challenge would give us anything intelligent. Like, I'm going to make this call already before we have it. Usually people make that call after you have a system like this. I'm already going to make that call. But I find it a super interesting challenge by itself. But he would argue that you still know the tasks that are coming at you. And you should build a system where you don't know the sort of tasks that are coming at you. Now, of course, in the ARC challenge, you know the task in the sense of you know the input-output format. But the logic behind the task you have to rapidly acquire. And I think that's like a subtle point he makes, but I think when he says you should pre-program human priors, he wants to say, because he defines these different kinds of priors, right? So he has like, oh, you have the reflexes that you get hit, you like flinch. We don't care about this. And then he says you have these objectness, navigation, and so on. Those you should pre-program. But then the last set of priors are the meta-learning priors, like your learning strategy. And that he considers that's intelligence. So, but I don't see I don't see a distinction between that and these other priors. Like if I could exactly formulate the meta-learning strategies that humans have innately, again, I would solve AGI. I find it pretty interesting because he himself, Chollet, goes and says, how would you solve something like this, right? In the paper, he has a section about what a solution might look like. And if you go to step 1 of that, it's like build a domain-specific language to capture all of the possible tasks. And so it's like create a programming language that creates programs whose outputs are these tasks. And then step 2 is like use the programming language to match, like find the program in that programming language that outputs the examples that you see of the task. And to me, it's like, how do you solve AGI? Step 1, build AGI. Because if I had a DSL that sufficiently outputs these tasks and narrowly enough so that it doesn't output anything, like not a Turing machine, then I would have already solved AGI or at least I would have solved the ARC challenge. So how do you build ARC challenge? Solve ARC challenge.
Isn't that the same as him advocating to build an expert system, which is precisely what he said we shouldn't do at the beginning?
Maybe, it's like, build a DSL and then match the DSL, sort of, I guess.
Yeah, it's tough. I suppose it comes back to Minsky's 1968 definition of AI, which is that it's the science of making machines capable of performing tasks that would require intelligence if done by humans. And I think that's a completely meaningless statement, by the way. That's the problem with intelligence, is you just can't get a handle on it.
Exactly, that's right. That's what I've been saying. At the end of the day, here, in Minsky's definition of intelligence, it contains intelligence, right? So, how much more washy can you be? And this, at the end of the day, you'll always be like, I don't know. I know when I see it, or something like this. It's like, and again, but we've come back to skill-based evaluation. That's what I said at the beginning. We're now at this ARC challenge, and again, it's a skill-based evaluation.
I think this is it. I think we're coming full circle, because we are now coming back to Minsky's view of artificial intelligence. So Minsky said the problem of intelligence would be solved if only we could encode human skills into formal rules and encode human knowledge into explicit databases. Because you said the number of priors as conceived by Francois Chollet is very small. And I think that there will be a compositional relationship between them. So if you take all of the grids that are on the test set on Kaggle, and you write a domain-specific language to generate many, many permutations of these, there must be at least some transfer to the grids that you've not seen.
Yeah, I mean, the interesting thing here is the fact that humans can solve all of them, right? And they've tested this, and their result is a reasonably smart human can solve all of these tasks without problems, without instruction, right? And of course, any system you build is going to have some carrying over because you've thought of some of the things, right? But the interesting thing is humans can solve all of them. And that means one of two things. Either, one, you haven't sufficiently been able to encapsulate these core knowledge priors and the meta-learning procedure that leads to this, or two, that in these tasks, there are actually more assumptions than are stated in the challenge implicitly. I don't know, but I'm going to count on a significant number being of the second sort.
It's really interesting because even now, when we're talking about solving this, we are doing exactly what Chollet said we would do, which is to find a shortcut. But if we did know about all of the priors, then it doesn't seem like it's even artificial intelligence anymore. It's something that you could just write using code.
That's my entire point. Because Chollet says you should explicitly list all of the priors that go into your intelligence test. And my point is, if you could explicitly list all the priors with sufficient detail such that you can make them formal, you would have already solved the problem.
What if you could generate many permutations of code and it would just be basic looping semantics that mutated things in the grid, and maybe you could model it as an agent moving around the grid, mutating cells that it was walking over or something. And you managed to, through this search space of possible bits of code, you managed to find a bit of code that would successfully mutate this cell into that cell.
Well, there's going to be, that's the exact difference to what you had on this DeepMind slide, right? Because there are going to be an infinite number of programs that conform to all of these examples, like infinitely many. I can always make a more complex program that also outputs these things, right? And even if you think like the simplest programs, there are going to be many of them that conform to that solution. I think this is what Chollet is trying to do, is he's trying to say, I am only going to consider solutions that humans can solve. And that's an entirely different thing, right? Because now, of course, when this green thing goes to the red thing, a human can solve that because, for whatever reason, we're like, oh yeah, going to something over, and these are the obstacles, of course. But if I tell you, no, actually, that's not it. The rule is actually the agent, you see, it always goes one diagonal and then one left. And then if the sum of the blue ones is 50, it turns this one green. And it just so happens to, in this grid, to make sense. I think, the focus of Chollet is whatever a human can do. Whereas I think what you had on the DeepMind slide is much more agnostic.
So this algorithm that I just wrote, is that an example of extreme generalization? In a way, it's not, because what I just created was something akin to quicksort. It's something that clearly could generalize to all of the analytically permutable instances of a particular grid, but it certainly couldn't generalize to any other task. And this is why Chollet believes there's a separation from the skill program, from the actual intelligence that created it. Now, one of the aims that Chollet had when he created this ARC challenge is to demonstrate the limitations of current techniques around artificial intelligence, especially deep learning. Deep learning simply isn't applicable here. Now, what's interesting is I could write a program which would generalize to all of the instances of that particular problem. But how do you write that program in a meta sense? How do you write the code that would generate that program? And that's called meta-learning. And Chollet is a huge advocate for program synthesis.
That's the field of program synthesis. However, today we just don't really know how to do it. So it's very much a graph search or tree search problem. Personally, I think genetic algorithms are very promising. So the one real-world application I'm aware of is flash fill in Excel. It's a way to automatically learn very simple programs to format cells in an Excel spreadsheet from a few examples. For instance, learning a way to format a date, things like that.
He thinks that program synthesis is the way that we can create algorithms that would incorporate the abstraction and reasoning capabilities which are not present in these deep learning models. Chollet thinks that the deep learning models are just doing very basic geometric interpolations, and they are fundamentally incapable of doing the kind of high-level reasoning that we need to do. So Chollet believes that the future of AI will be recomposable modules that are a bit like computer programs, and these programs will represent the kind of priors and reasoning that we humans do. He thinks that there'll be algorithmic modules for doing things like planning and searching and reasoning with a specialization around certain tasks, like for example doing geometry. He thinks that these modules could be automatically recombined using some kind of meta-learning algorithm.
You would have this sort of program synthesis engine that would have access to a large library of primitives, of subprograms. And some of these programs will be algorithmic in nature, like tree search, for instance, like Monte Carlo tree search. And some of them would be geometric in nature.
He thinks that when we have a big enough library of these modules, that in a way will create a kind of artificial general intelligence that could be compared with human intelligence. So he says that this vision of having all of these recombinable modules is how we will get to artificial general intelligence. But he's very clear that we should have an anthropocentric view of artificial general intelligence. The zombie apocalypse coming anytime soon. Chollet is a staunch believer that there's no such thing as an intelligence explosion. And we'll get onto that next. Of course, coming up with a meta-learning algorithm for program synthesis, it's so much harder to train these things because it's not differentiable. So you might be looking at some kind of evolution strategy to create that. Several public intellectuals, notably Sam Harris and Elon Musk, have used quite a lot of hyperbolic language about artificial intelligence.
We continue to improve our intelligent machines year after year after year. And at a certain point, we will build machines that are smarter than we are. And once we have machines that are smarter than we are, they will begin to improve themselves. And then we risk what the mathematician I.J. Good called an intelligence explosion, that the process could get away from us. Now, this is often caricatured, as I have here, as a fear that armies of malicious robots will attack us. But that isn't the most likely scenario. It's not that our machines will become spontaneously malevolent. The concern is really that we will build machines that are so much more competent than we are that the slightest divergence between their goals and our own could destroy us.
Don't get me wrong, I love Sam Harris and Elon Musk. They are great guys, but they are horrifically misinformed when it comes to artificial intelligence.
So intelligence explosion, I'm sure you're familiar with the idea, but it's the idea that if you were to build general AI problem-solving algorithms, well, the problem of building such an AI, that itself is a problem that could be solved by your AI, and maybe it could be solved better than what humans can do. Right. So your AI could start tweaking its own algorithm, could start making a better version of itself, and so on iteratively in a recursive fashion. And so you would end up with an AI with exponentially increasing intelligence. Even humans, not even talking about AIs, I don't think their brain and the performance of their brain is the bottleneck to their expressed intelligence, to their achievements. You cannot just tweak one part of this system, like of this brain, body, environment system, and expect the capabilities, like what emerges out of this system, to just, explode exponentially. Because anytime you improve one part of a system with many interdependencies like this, there's a new bottleneck that arises.
So this is fascinating. Chollet believes that intelligence is a bit like a latent variable, or it's not really something which should be a first-class citizen. It's something which emerges from a constellation of interdependent factors. Chollet gives the example in his Measuring Intelligence paper of your physical fitness level. It's actually comprised of many different factors, like, for example, your cardiovascular fitness and your health and your diet and how much sleep you've been getting and how long your legs are. There are so many factors together. What is interesting about intelligence, and we spoke about this on the Street Talk podcast, is that there seems to be one general quotient factor of intelligence. You might expect it to be fairly heterogeneous. My personal opinion on that is because many of the cognitive tasks that we do have interdependencies. For example, if you have a poor working memory, you would probably be quite impaired at doing many cognitive tasks.
It considers intelligence as a property of a brain that you can consider in isolation, like the height of a building, for instance.
Right.
But that's not really what intelligence is. Intelligence emerges from the interaction between a brain, a body, like embodied intelligence, and an environment. And if you're missing one of these pieces, then you cannot really define intelligence anymore. So just tweaking a brain to make it smarter and smarter doesn't actually make any sense to me. I think people who talk about things like intelligence explosion tend to focus on one agent is basically one brain, like one brain considered in isolation, like a brain jar that's controlling a body in a very like top to bottom kind of fashion. And that body is pursuing goals into an environment. So it's a very hierarchical view. You have the brain at the top of the pyramid. Then you have the body just plainly receiving orders. And then the body is manipulating objects in the environment and so on. So everything is subordinate to this one thing, this epicenter, which is the brain. Right. But in real life, intelligent agents don't really work like this, right? I do believe all intelligence is specialized intelligence. Even human intelligence has some degree of generality. Well, all intelligence systems have some degree of generality, but they're always specialized in one category of problems. So the human intelligence is specialized in the human experience.
According to Chollet, the intelligence of a system is a measure of its skill acquisition efficiency over a scope of tasks with respect to priors, experience, and generalization difficulty. This is a load, so let's unpack it. The intelligence of a system, so this is the measure we're actually talking about, is a measure of its skill acquisition efficiency. So that means that intelligence isn't just skill. It's not just that you are really good at a task. It is that you are very efficient at acquiring skill over a scope of tasks. So that means we have to define which tasks we want our intelligent system to be over. Chollet expresses that all intelligence must be measured relative to a scope of tasks, and he suggests that the human scope of tasks would be ideal to measure machine learning systems, which makes sense. It goes on, it says, with respect to priors, experience, and generalization difficulty. So these are the three things that we'll have to quantify. Prior is anything that the developer of the system builds into the system. So in a convolutional neural network, this would be translation invariance. In a bag of word model, that would be the fact that the order of the words doesn't matter. You can also think of the prior really differently for classic applications. Any classic software program is made entirely of priors. So your calculator app is really, really good at calculating. That doesn't mean it's intelligent. It just means it has a lot of priors. Experience is what the system can learn from a limited data set. So this is your classic machine learning problem. You have a limited data set. What can you learn from that data set? Experience specifically references how large is that data set. If you have lots of experience, you're going to be very good at a given task. That doesn't mean you're intelligent. That just means you have lots of experience. And third, the generalization difficulty refers to how hard is it to solve a task given experience. So for tasks A and B, you could be given the same amount of experience, but with the amount of experience for task A, you're able to solve the task in pretty much any situation. But task B requires significant generalization, and therefore the generalization difficulty is harder because the same experience isn't sufficient to solve all of the task. So if you come from classic machine learning, you might think of an intelligent program as this part here on the right. The intelligent program for a given task means that it's given a situation, for example, a data point, and its response is really, really good. This is your classic ImageNet classifier or AlphaGo reinforcement learning Go playing bot. It has really high skill because it's really good at a particular task. But Chollet says this is not intelligence. What is intelligent is the system that makes the skill program. The act of generating a skill program and incorporating feedback of how that skill program performs in order to then generate even better skill programs. That's intelligence.
So measuring skill can be one proxy across many different tasks. It can be one proxy for measuring intelligence, but if you want to only measure skill, you should control for two things. You should control for the amount of experience that your system has and the priors that your system has. Right. But if you control If you look at two agents and you give them the same priors and you give them the same amount of experience, there is one of the agents that is going to learn programs, representations, something, a model that will perform well on the larger chunk of experience space than the other. And that is the smarter agent.
So the intelligent system necessarily needs to be viewed as a system that creates skill programs and not the skill programs itself.
This is part of what the way to our office looks currently. And you might ask yourself, what determines whether or not I can plan my way through all of this mess right here? Is that intelligent behavior? Now, Chollet makes a difference between prior skill, experience, and intelligence. In this case, probably evolution has endowed me with the ability to plan my way through any uncomfortable terrain. So Chollet says that might not necessarily be intelligent because it's already built into you. Intelligent is only what comes on top of A, things that have been built into you, and B, things that you have experienced a lot. Which means that even if evolution wouldn't have taught me to do these kind of pathfinding missions, I could still have done so lots and lots and lots and learn from lots of data. That wouldn't make me smart. That would just make me a very hard learner.
We now come up with a formal definition of the quantities we need to define intelligence. First is the generalization difficulty. This is supposed to measure how difficult is it to generalize a task. That means how difficult is it to solve a task completely, such that you understand the task and you can solve any given situation that might arise in a task from two things. So it measures how well can you solve a task. So what we're actually measuring here is H, the entropy, or in this case, it is the description length of programs. Now, we're normalizing here by the description length of the shortest program that is able to solve the solution to task T, and the theta here is a skill threshold. So we want to solve the task T to a given skill threshold, and we need at minimum a program of this length for it. The numerator here is made up of two parts. Again, we want the solution to the task, but we condition on two things. Namely, this here is the length of the training solution, the optimal training solution to a given curriculum. So this here is your machine learning system that has completely optimized on the training data set. While this here means the intelligence system at time 0. This is any prior that the developer has built in. Let's write this with a little human here. So the human will incorporate its own knowledge about all the tasks into the intelligence system at time 0. That is the prior knowledge that is available. This here is the knowledge that is available from the training data set. So Chollet views these two things as given the knowledge I have from my developer and from the training data set. How difficult is it to then come up with the solution for the entire task? If that difficulty is high, it means that the training data set as well as the developer haven't really given me enough information to solve the task. Therefore, its generalization difficulty is high. But if this here is 0, that means that either the training data set or the developer has input information that basically makes solving the task as a whole really easy. The generalization difficulty is not very high. The second quantity we need is the prior. The prior here isn't a distribution like in Bayesian optimization. The prior, it says here, can be interpreted as a measure of how close from a sufficient or optimal solution the system starts, i.e. the amount of relevant information embedded in the initial system. We've seen most of these quantities before. So H sol T here is the length of the shortest program that solves the entire task. Think of the calculator app in order to solve basic math. The code needed to write that application, that's the shortest program to solve the task in general. What we're wondering is if we are given input from the developer, how much more work is it to come up with the solution for the entire task? So if the human here has already programmed the calculator app, the generalization difficulty for solving basic math is 0. But if the human hasn't really input anything, just sort of a deep neural network, and we're trying to solve basic math, the prior here, the difficulty of coming up with the solution is very high. And therefore, since we are subtracting here, the prior knowledge is very low. So the prior here in general is a measure of how much information the developer has built into a given system at the beginning. The last quantity we need is the experience. The experience of an intelligent system at time step t for a task capital T is simply how much closer to a solution the intelligent system is if given a piece of data at time step t. So think of a machine learning system. It basically means how close is the machine learning system at time step t to the general solution of the task. And now you input one piece of data. Now given that data and the previous state, how close are you now? The difference between those two measures is your experience at time step t. The more experience you have, the closer you're going to get to the final solution. And the total experience of a system over a curriculum is simply the sum of all the experiences in all of the time steps. So basically you can see this as how much information can you extract from a training data set. Now we're ready to define intelligence, and we'll just focus on the sufficient case up here. So intelligence of a intelligent system IS, given a scope of tasks and a skill threshold for each task. We have a bunch of expectations in here. So these are weighted sums. The first weighted sum goes over the scopes of tasks. So we're basically summing up across all tasks we're interested in. And each task is weighed by how important we think achieving a given skill in that task is. Within each task, we consider every possible curriculum. That basically means we consider the distribution of training data sets that are possible for that task, if you think of machine learning system. For each training data set, we multiply its probability, so this quantity is in effect is an expectation, by the following quantity. And here is the measures that we've defined previously. The intelligence is high if the generalization difficulty of that task in that curriculum is high. The intelligence is generally lowered by the following two quantities: the more priors you have and the more experience you have. That means if it is very hard from a given training data set to come up with the general solution of the task, then the task is very difficult, and the system that can solve that task is very intelligent. However, if the developer has already built in lots and lots of information into the system in order to solve the final task, then the system is less intelligent, the more priors the developer has built in. Further, if a system has had lots of experience and reaches the exact same generalization capability as a different system, that also means it's less intelligent, because the other system is better at turning less experience into the same skill. So these three quantities pull on this measure of the intelligence, and together across all training curricula, for all the tasks you're interested in, they make up intelligence.
In this definition, it is already very obvious that intelligence has to be specialized, because you're talking about experience space. Right. You're talking about segments of experience space. You're talking about priors, and you're talking about experience. All of these things define the context in which intelligence emerges. And you can never look at the totality of experience space, right?
So what then is a real display of intelligence? In Chollet's framework, intelligence is something that your priors and your experiences do not prepare you for. If you have a problem that's this hard, and your prior knowledge and all your experience to date only get you this far, the difference is what you have to use intelligence for. And therefore, if we measure intelligence, we should look at all of these quantities. We should look at how hard is the task, and to which part can your prior experience and also your data that you have collected so far help you in solving the task. Whatever's left, that's intelligence.
Do you guys think that we are fundamentally going in the right direction on AI research? I think that in many ways we're wasting our time.
I would say humans, as a result of developing the kind of AI that we're developing, have gotten so much smarter. I have a phone, and with the phone, I am 100 times smarter than without the phone, right? So I'm not more intelligent than before. The phone, apparently, according to all of these definitions, isn't intelligent by itself. But with the phone, I can outsmart anyone. So I think we're very much going into the correct, actually even a better direction than AGI, because AGI is like going to singularity and we're becoming obsolete. The way we're developing AI is that we make ourselves so much smarter.
In philosophy, that's known as the extended mind. So your phone and the internet is an extension to your mind, and you can access this wealth of information. But if you think about the growth of capability, it must be limited. So now you have all of this information at your fingertips, all of the information the world has ever known. And what it does is it makes you more efficient at achieving certain things in certain situations. What are your final takes on Chollet?
I think it's a noble attempt at defining intelligence and making an intelligence benchmark. I think that in some ways this attempt has failed because we're not smarter after this. And intelligence remains something where the only way to define it is I know when I see it. It just remains, or because either you can't measure the quantities that he's proposing, or if you go to something like the ARC challenge, I seriously doubt that, for example, he has listed all of the priors that go into it. And I seriously doubt that when the ARC challenge is solved, that anyone would be convinced that this has anything to do with intelligence. And I think it will remain the I know it when I see it. And lastly, I think this criticism of deep learning or generally machine learning as, oh, it's just skill and it's not real intelligence. It's true, but I think it's the wrong way of thinking, sort of the wrong way of thinking about it, in that I think something like AlphaGo is incredibly smart if you factor in the people. And I don't mean this in the way that Chollet says, well, it's just a people program. No, I mean the symbiosis, the generalization capability of the DeepMind team plus the computers they have is immense. Yeah, that's.
I see. So you're saying that we should see them as one whole.
Yeah, I think that process, in terms of generalization capability, if we're looking at that symbiosis is one of the most generalization capable that we have. And you can't go measure this with any kind of psychometrics or anything.
So do you think at university they should teach Hutter and Legg's definition of intelligence, or Chollet's?
Well, probably neither. I like this paper a lot, but I think for any practical purposes, it's like a nice academic exercise. But I doubt this has any consequential, not even practical applications, but I doubt this has any consequences at all.
Well, I like this function of like priors, experience, generalization, difficulty. I think that is a useful way of thinking about any of these problems.
Remember to like, comment, and subscribe, and we'll see you back next week.